Let's wrap up these problems on half-life. In number 5, after 20 days, a 120 kilogram sample of bismuth-210 decays down to just 7.5 kilograms. What is the half-life? Again, you can do these with a table, you can do them in your head. I kind of figured, all right, let's plot the half-lives, and I filled in the time afterwards. I did that last. After the first half-life, the 120 kilogram sample would be down to 60. The second half-life, I'd be down to 30. The third half-life brings me to 15 kilograms, and it's going to take me 4 half-lives to reach 7.5 kilograms. At that point, they do tell you that the time passed has been 20 days. So 20 days is 4 half-lives. 20 divided by 4 must make each half-life 5 days. That's not so bad. I mean, you could do this in your head. You know, you can count on your fingers. The first time I cut it in half, I'm down to 60. The second time, 60 goes to 30. The third time, 30 goes to 15. 4 half-lives. 15 goes to 7.5. 20 days divided by 4 is your 5-day half-life. I really like number 6. It kind of summarizes everything that we've been looking at in terms of half-life. And it puts it in terms of percentages. What percent of a sample of radioactive element whose half-life is 5 years, what percent will decay after 25 years? What percent is gone? What percent has decayed after 25 years? Well, they might also ask this in terms of how much is remaining. So I thought, hey, why not plot both of them? So I have my half-lives, my time. Each half-life is 5 years. Then I did percent that remains and percent that has decayed. So for example, like in number 5, after 20 days, this 7.5 kilograms, that's the amount that remains. If I want to know the amount that has decayed, I would take the original 120 and subtract 7.5. So let's do both of them. For any isotope, after the first half-life, you're down 50-50. 50% has decayed, 50% remains. And in this case, that would be 5 years. It's going to take me 5 half-lives to get down to 25 years. So I said, all right, after the second half-life, 10 years have passed. 50% of your remaining isotopes are gone. So my 50% goes down to 25% remaining, which means 75% decayed. After the third half-life, 25% remaining goes down by half. Now 12.5% remains, 87.5% is gone. And you just keep doing that. The percent remaining and the percent decayed should always add up to 100. And so finally, after 5 half-lives, 25 years have passed, about 3% of my sample remains, and approximately 90% has decayed. This would be true of any sample. And so again, if you needed to jot anything down, feel free to pause the video at any time and get what you need. Before moving on to this last part, I really like this graph. We're going to use this to answer questions 7 through 10. This graph is of carbon-14, a radioactive unstable form of carbon. It's plotting the percent of carbon remaining versus time elapsed. How many years have gone by? So I originally start with 100% of my particles remaining. After, look at this, 5,730 years, my 100-gram sample, or my 100%, has gone down to 50%. Which, again, you could figure that maybe this was like a 100-gram sample. Now it's down to 50 grams, or 50% remaining. So they ask in number 7, how long is a half-life? It's the time for the original sample to decay by half. It is 5,730 years. Here's my first half-life. If only 25% of the carbon-14 remains, how old is the material? Okay, so let's look at this graph. A lot of these answers come right off the graph. My 100% goes down to 50. That's the first half-life. Here would be 25%. 25% is the second half-life. Or in other words, 11,460 years. It takes 2 half-lives. And so again, for any sample after the second half-life, 25% remains. Number 9. If a sample originally had 120 atoms of carbon-14, how many atoms will remain? Interesting. After 17,190 years. Now again, having 120 atoms is a little crazy. We could never even measure 120 atoms. But on a smaller scale, we can figure this out. Okay, so this 17,190 years, that is on the chart here. That must be the third half-life. Now, a few ways that you could solve this. It's not listed, but this right in here, if I follow it across and down, this would be half of your 25%. Or in other words, 12.5% remaining. So you could say I'm going to have 12.5% of my original sample. You could take your 120 atoms and you could multiply by 12.5% or 0.125. I plug that in my calculator. I get 15 atoms. There's one option. Or option 2, you could say, well, this is 3 half-lives. So the first half-life would bring my 120 atoms down to 60. The second half-life would go 60 down to 30. After 3 half-lives, 30 atoms would decay to 15. You get the same answer either way. And finally, number 10, if a sample known to be about 11,460 years old has 400 atoms of carbon-14, how many atoms were originally in the sample when the organism died? This carbon-14 radioactive carbon is used in carbon dating, where we can look at the amount of carbon remaining in the sample, and knowing the half-life, we can kind of backtrack and figure out how old the sample was when it died, or when the sample was must have decayed or died. Okay, so if I look at this graph, I can kind of tell that the 11,460, that would have been after the second half-life. So let's work backwards and figure out the original amount of carbon in the sample. So I'm going to plot on my graph. After this 11,460 years, right in here, this was 400 atoms. So let's backtrack. After the first half-life, then this must have been 800. And so sometimes people will say, cool, 800, that's my answer. Well, that 800 is after 5,730 years. That's after the first half-life. The original would be double that. The original sample must have had 1,600 atoms. I just worked backwards. I would be able to understand this half-life off of a graph. Use the graph to figure out the half-life, figure out the age of a substance, how many atoms remain, how many atoms have decayed. And then also we could do it just from a short answer kind of problem like the other ones.